Hello, hello.
Hello, Dr. John. How's it going?
Hey, good. How are you?
Good. Had a midterm today.
Ah, how'd it go?
Yeah. I think it went pretty well. Yeah.
That's good. That's good.
Yeah. Like before the midterm, we had like a study sesh with some classmates,
Uh-huh.
and we were just reviewing. It was straightforward though.
Okay, that's good. That's good.
Yeah.
Always a good thing to have a good midterm experience.
Mm-hmm. And I'm just currently grinding on the homework.
Mm.
How you doing, Dr. Chan?
Hey Eddie, good. How are you?
I'm tired as usual.
Yeah, hang in there.
How's your week going?
That's good. Yeah, I saw a doctor today. First time in a very long time. I think the last time I had a general checkup was maybe back when I was in college, actually.
Oh,
So it's been a really, really long time. Yeah, my blood pressure is a little bit high. It's pretty high actually. I need to work on that. But the main reason I went was because I've been having a lot of back pain. And so it's been persisting for 3 weeks now. And so I went to go get it checked out. So the doctor thinks it's a muscular thing. And so he recommends just icing it. And so I found out today that it looks like a lot of the pain is actually radiating from my butt. And so I think I pulled a muscle there. And so you can't see it, but like I don't have any pants on right now, and I'm like sitting on an ice pack. And so that's been making me feel a lot better actually. One of the perks of working from home.
looks like you got to stretch more.
Yeah, I definitely got to stretch more too. Yeah.
So other than that, everything's good.
Yep. Yeah.
Nice.
Are you going to commencement?
I am. Yep.
Okay.
Yeah, I won't be on stage, but I'll be one of the I think they call them marshal. And so I'll be just guiding people up to the stage and just doing just general crowd control.
Oh, I see.
I was joking with my grad students because their project is due on the day of graduation too. And so they asked if they could ask me questions on the project at graduation. I said, yeah, if you bring your laptop to graduation, I can help you debug your code while we're waiting to walk up.
That's hilarious.
That's funny. We'll see if that's true though. I'll hold you up to it.
Yeah, it's open to you guys too. And so if you guys are walking, you bring your laptop and you say, hey, can't get past this error. Yeah, I'll help you out right there.
Ain't no way. I'm gonna be drunk for sure. Yeah, I actually applied to be the commencement speaker.
Oh, nice. Very nice. I always miss the memo. I mean, I've been a part of a lot of graduations now. One for my undergrad, for my master's, and for my PhD. And I always missed the memo on that. And so I never got to apply for that. But I would have loved to apply for it too. But I always miss the memo.
You should all take a picture together.
Yeah, for sure, for sure. Yeah, I was at the graduation last year too, but I think a lot of people didn't recognize me because I had a mask on and sunglasses. But a few people did, and then we took pictures. It was weird because a lot of the students I didn't know what they looked like just because it was the whole pandemic, and so they recognized me, but then I didn't recognize them, and so we had to kind of do an awkward introduction again.
Oof.
But that's the reality of virtual instruction. All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. Thank you, everyone, for joining virtually today. You know, I know it's kind of a last minute thing, so I appreciate you guys' flexibility. So how's everyone doing today?
Pretty good.
Good to hear.
Yeah, usual.
Projects.
Yeah, I know it's a busy time, so I know there's dozens of projects that you guys are working on. So Yeah, definitely. This is the crunch time for the semester. Okay. So the plan for today is we're going to finish up our lecture notes on convection with finite volumes. Maybe not finish up, but we'll at least make some good progress on it. Okay. And then we'll see how far we get. All right. So remember, the midterm is going to be next Wednesday. And so if you didn't get the announcement email, I did send out an email with the study guide for the midterm, as well as a poll. And so we're going to do the same thing we did for the first midterm. And so I'm going to have you guys vote on the topics you feel most uncomfortable with, and then I'll do a review video on Friday to help you study. Okay. In terms of content, it's just going to be based on the material that we covered since the first midterm, and so that's going to be unsteady problems and diffusion with finite volumes. Yeah. Okay. Oh yeah, that's right. I pushed it back. That's right. Yeah, the midterm is going to be next Monday, so it's going to be 4:25. But the content for the midterm is going to be the same. And so because I already had everything prepped for the study guide and the review video, that's all that's going to stay the same. And so we push the midterm back, but the content on it is going to stay the same. Yeah. And so please vote in the poll. And so, I think I will still film the review video this Friday, just because, I have the time for it. And then you'll have that available all next week for you to study. Okay. And in terms of homeworks, the only homeworks that will be covered on the midterm are homeworks 4 and homeworks 5. So homework 4 was the homework on unsteady problems, and homework 5 is the one you're finishing up today. That's the homework on diffusion with finite volumes. And so make sure you study both of those for the midterm. Okay. Okay. And so are there any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. And so I believe we left off right before I wanted to do an example. And so we covered, finite volumes in 1D for our convection diffusion equation. We did standard central differencing, and we did upwinding. And so now let's go ahead and put it together in an example so you can see how it all fits together. Okay. And just like is tradition, we'll do part of this example by hand, just so you can see me derive the equations like that. And then we'll move on to the code so you can see how this is implemented there. Okay. Okay, so here's our example. And so we have our standard 1D equation. Okay. And so our 1D equation here is we're going to have 5 d phi dx. I don't know why I have u here. It's weird. 5 d phi dx minus 8 d squared phi dx squared. And this is equal to 3x. Okay. The domain that we're looking at is between 0 and 1. And so we have 0 is less than or equal to x, which is less than or equal to 1. Okay. And of course, we need our 2 boundary conditions. And so we're going to have a Dirichlet boundary condition on the left. And so we have phi of 0 is going to equal 1 or 10. And then our other boundary condition is going to be a Neumann boundary condition. And remember, for now that we're looking at both convection and diffusion with finite volumes, we are redefining our Neumann boundary condition. And so instead of specifying the derivative of the solution at the other side of the domain, we're saying that we're going to specify the flux instead. Okay. And you'll see what that looks like mathematically for this example. Okay. And so what we say is the flux of the solution at x is equal to 1, that's going to equal to 3. Okay. Okay. And we're going to solve this equation on a finite volume domain with 4 cells. Okay. Okay. And so this is going to be cell number 1, this is going to be cell number 2, cell number 3, and cell number 4. Okay. Okay, so before we get started, let me go ahead and mark the center line coordinates, okay, or the cell center coordinates, right? Because remember, we're going to need them to specify our source function here, and so the coordinate for the first cell center is going to be 0.125. Okay. For the second cell center, we have 0.375. For the third cell center, X3, we have 0.625. And then for the fourth cell center, it's 0.875. Okay. Because the whole domain is has length 1, and because we have only 4 cells, the length of each cell is going to be 0.25. Okay, and so that tells us that the grid spacing delta x, right, or the distance between cell centers, is also going to be 0.25. Okay. And before we get started, let's go ahead and write down the problem parameters. Okay. We're just going to read these just straight off the problem. And so first one that we notice here is the convection velocity u. Okay. Remember, u is the coefficient that's in front of the first order derivative. Okay. And for this problem, that number is 5. Okay. Next, we have the parameter value for the diffusion coefficient. Okay. And this is the coefficient in front of the second order derivative. And be careful here, because normally when we view the diffusion term, when we have both convection and diffusion, it's usually on the other side of the equation, right? It's usually on the same side as the source. And so since we moved it to the other side, I think it's tempting to put k is equal to -8 here. But for this problem, k is just going to be just regular 8, okay? Because this negative that you see right here, this negative right here, this is a result of just the equation itself. And so it's not a negative diffusion constant. It's just a negative that's built into this equation. Okay? Right, so those are our two parameters, and so that's our convection velocity and our diffusion coefficient. And we can also specify what the source term looks like. And so the source term here is just the term that's on the right that doesn't involve phi, okay? And so that's going to be 3x. Okay. Okay, and so just like we always do with these kinds of equations, we are interested in writing out the algebraic equations that we can use to solve for the finite volume solution. Okay. Okay, so we're going to go through the process of deriving those, in this case, 4 equations, because we have 4 cells, and so we need 1 equation per cell. Okay. All right. Any questions on this? Okay. All right, so let's go ahead and write out the general equation for the interior nodes. Okay. At this point, we have to make a decision on what kind of differencing scheme we want to use for the convection, right? Right, so just like we had in finite differences, we have the choice here of either one, and that choice is motivated by the Peclet number, right? And so if we compute the Peclet number for this case, the Peclet number is the velocity multiplied by delta x, and we're going to divide by k. Okay. And so let's go ahead and plug in for all these variables. And so u here is 5. Okay. Delta x is 0.25. And if we divide this by 8, okay, what we get is 5 over, we have 1 over 4 times 8, 32. Okay. And so here we have something that's less than 1, and if it's less than 1, it's less than 2, right? And so what this tells us is that if we use a central scheme, then our solution will be stable. Okay. So let's go ahead and use that because, if we can use the central scheme, it's always, a lot more accurate. And so that's preferable for us. And so under the central scheme, right, under the central differencing scheme, we have the following equation for the interior node, for the interior cells. Okay. Right, so our equation is minus u divided by 2 minus k over delta x multiplied by phi of the left neighbor. Okay. Then we have 2k over delta x. This is multiplied by phi sub c. Okay. And then plus we have u divided by 2 minus k divided by delta x. Phi sub r, the right neighbor. And on the right-hand side, we just have the trapezoidal rule evaluation of the source term. And so that's q of xc multiplied by delta x. Okay. All right, so let's go ahead and plug this in for cells 2 and 3. So those are our interior cells. Okay. And so if we do that, we have cell 2, right? We plug in all the numbers. We have a minus 34.5. Phi 1, which is the left neighbor, plus 64. Phi 2 minus 29.5. Phi sub 3. Okay. And this is equal to our source term. And so our source term here is 3 times x. Okay. And so if we multiply by delta x, our delta x here is 1/4. And so we're going to have 3 over 4. Okay. And we're going to multiply this by x2, right? Because since our q of x here is 3x, and so our q of xc here would be 3xc. Okay. Our xc for node 2 here, you can see is 0.375, right? And so let's go ahead and plug that in here. 0.375. Okay, so that's cell 2. And so cell 3 is going to be very similar. And so cell 3 is going to be a minus 34.5. Phi 2 plus 64. Phi 3 minus 29.5. Phi 4 is equal to 3/4. Except now we're going to multiply this by x3. And x3 is 0.625. Okay. And so that's 2 of our 4 equations down. So these are the interior node equations, right? And so these would go directly into our matrix. All right. Any questions on this? Okay, so those are our 2 interior cells. And so let's go ahead and work on our 2 boundary cells. And so let's start with cell 1. Okay, and so cell 1 here is connected directly to the Dirichlet boundary condition. And so we need to account for that in our equation. Okay. And so let me do this. Let me take our finite volume equations and let me kind of take them a couple steps up, up until the point before we plugged in for each of the expressions. Okay. Okay, and so if you kind of follow our derivation in reverse from Monday, you get the following expression. So we have u times phi minus k d phi dx. Okay. All this is evaluated at the right neighbor, okay, or at the right border, excuse me. And then we have u phi minus k d phi dx. Okay. And all this is evaluated at the left at the left border, okay? Right, and that's going to equal to 3/4 times the x coordinate xi, okay? Oops. Oh wow, we went all the way up to the beginning. Okay. All right, and so we need to and so we need to modify this equation to account for the boundary conditions. Okay, so we know the boundary condition occurs on the left, right? And so the integral that has to do with the right, or the integral term that has to do with the right side, we're going to leave that unchanged. Okay, so this guy will remain unchanged. Okay. Meanwhile, this guy has to be modified to account for the Dirichlet boundary condition. Okay, so let's start with the part unchanged right now, just to kind of give us a reminder of how we actually do this. Okay. And so for the part unchanged, we're going to plug in our linear approximations for the boundary phi terms. Okay. Okay. And so if we do that, what we get is we have u multiplied by phi at the right boundary, and so this is phi sub r plus phi sub c divided by 2. Okay. We're using a central scheme here, and so it's just going to be the average. Okay. Oh, question. So how do we know which term will be changed? Yeah, it's a good question. And so the term that should be changed is whichever one borders the boundary. So we're doing this for cell 1 right here. And so if you go back up to the problem definition, right? If you look at cell 1 is this one right here, right? According to the problem statement, just 2 lines above, what we have is we have a Dirichlet boundary condition of 10 applied right here. Okay. And so since that occurs on the left side of the cell, that means we need to replace the integral terms that have to do with the left side. Yeah. Meanwhile, the one on the right will be unchanged because we have a neighbor that's on the other side of that cell. Okay, so that's going to be cell number 2. Okay. And so that's the part that you get that remains unchanged. Okay. And for this part, we have to modify it to account for the Dirichlet boundary condition. Okay. And so first we have u times phi evaluated on the left edge of the cell. And so that's going to be u times phi naught. Right. And so phi naught is the Dirichlet boundary condition. And so remember, in finite volumes, our cells themselves are not sitting on the boundaries, but their edge values are. Okay. And so when you evaluate the the phi terms at those places, you have to just plug in the Dirichlet boundary. Okay. Right, and then we have k. And so for k, or for the diffusion term, we have phi sub c minus phi naught. Okay. All divided by delta x over 2, because we only travel a half, half distance to get to the other side. And then on the right-hand side of the equation, we still have our usual source term. Okay. All right, so now that we made the appropriate substitutions, we can go ahead and rearrange it. And so everything that has a phi or an unknown phi value, we're going to move to the left. Okay. Okay. But all of the known quantities, and so this includes the source term, the source term, as well as the Dirichlet boundary condition term. And so those are going to move to the right. Okay. And so if we do that, we end up with the following. And so we only have on the left-hand side, we don't have a contribution of phi from phi L because there's nothing over there, right? It's just an empty, that's just the boundary. And so the first entry we have here is for phi sub c. And so we have u divided by 2 plus 3k divided by delta x. Okay. This is phi sub c plus the contribution from phi sub r. So this is going to be u divided by 2 minus k over delta x, okay, times phi sub r. Okay. And on the right-hand side here, we have our source term as well as our boundary conditions. And so first we have our source term, and so that's 3 over 4 xi. Okay. Then we have a contribution from the from the diffusion term, and so this person right here. And so it's going to be plus u theta naught. Okay. And then we also have a contribution from the diffusion term as well. Okay. So let's see, we have 3 negatives, and so that's going to make a positive on this side. Okay. And so this is going to be 2 times k divided by delta x times phi naught. And so we're now at a point where we can just go ahead and plug in numbers. All right, so we plug in numbers, we end up with the following expression. Okay, so remember this is for cell 1. And so for cell 1, we have a 98.5 V1 minus 29.5 V2 is equal to 3/4 times 0.125 plus 30 plus 64. Okay. Okay, so that's how we deal with the Dirichlet boundary condition. I know we've done it several times now, but it's always good to practice a bit more because there might be some nuances or a sign change that you don't catch unless you actually work it through from the beginning. Okay. All right, any questions on this? Okay, all right, so that takes care of the Dirichlet boundary condition. Now let's look at the Neumann boundary condition on the right. Okay. And so first thing we notice is that we only have one cell that borders the right side of the domain, and that's going to be cell 5. Okay. Okay. And so let's start out with the same place that we started out the Dirichlet boundary condition, and then we'll go from there. Oh, excuse me, cell 4. Yeah, there's only 4 cells. Okay. And so starting from the same place that we started the Dirichlet boundary condition, we have a u phi minus k d phi dx. Okay. All this is evaluated at xr. Then we have minus the same thing, but evaluated at the at the right, excuse me, the left edge. Okay. Why do I keep doing that? Okay. Okay. And so we're on the rightmost side of the domain. And so that means that our left contributions that go to the left neighbor, those are going to remain unchanged. Okay. And so that means the right side, which is the side that borders the Neumann boundary, this is going to change. Okay. And so we're going to change it to adjust for the given flux that's given to us. Okay. And so what we're going to do is we're going to replace this entire integral here with our, with our source variable. And so our source variable here, we'll call it gamma, right? And so all we have then is we have gamma minus, we have u times phi itself evaluated at the left edge of the cell. And so that's going to be phi 4 plus phi 3 divided by 2. Okay. And then we have a minus k phi 4 minus phi 3 all the way down to x. Okay. And this is equal to 3 over 4 x I. Okay, so let's go ahead and plug everything in. Okay, so we're going to plug in and rearrange things. And so for cell 4, what we get is a minus 34.5 phi3 plus 29.5 phi4 is equal to 3/4 times x4. And so x4 here is what? X4 here is 0.875. Okay. And then we need to add our Neumann contributions as well. And so basically we're going to move this term over to the other side of the equation because it's a known quantity, right? And so because it's given to us, it's known. And so if we do that, we see that our Neumann condition here is, where is it? 3, right? And so the flux on the right side, on the very right side of the domain should be 3, okay? And so that lets us plug in 3 for that. And so we put it all together. This is the equation that we obtain. Okay. All right, any questions on this before we jump into the MATLAB? Okay, all right, so let me go ahead and jump into MATLAB and I'll show you the MATLAB implementation of this code right here. Okay, so this code is posted for you on Canvas, and so you can view it as the 1D convection diffusion code, right? And let's go through this kind of step by step and see, what's going on here. Okay, and so the first thing you see is that we're defining all of our variables. Okay, and so we have our number of cells, we have the coordinates, we have the coordinates of the centroids, we have the grid spacing, we have the diffusion coefficient, convection velocity, and I also computed the Peckley number here just to make sure that we're stable. Okay. Okay, and so just like all of our other finite volume codes, we're going to write a loop. And so that loop is going to visit every single cell, right? And then depending on the value of I cell, that's going to tell us where we are in our traversal of every single element. Okay. And so first, let's do the case when I cell is equal to 1. And so this is the case when we're bordering the Dirichlet boundary, or our left side or our left edge is on the Dirichlet boundary. Okay. Oh, yes, I can definitely zoom in. Sorry, I'm on my, forgot that I'm on my home computer here. Okay, is that better? Okay, good. Okay, and so let's see how we deal with the Dirichlet boundary, right? And so if we have the Dirichlet boundary, we follow the same rules as we did before, and so we make the adjustment. And so for the velocity term, the velocity term actually stayed the same, and so we end up with a 1/2 u multiplied by both of our both of our contributions here. Okay, and then for the phi sub c contribution, we end up with a 3 times k divided by dx. Okay, remember we increased this contribution by 1 because of the Dirichlet boundary, right? And then our neighboring cell, which is the right cell, then we have just a minus k over dx, right? So this is pretty standard. The only difference here is that we don't have a left neighbor contributions, right? And so we only have right because of that. Okay, and then after that, we have to add together the right-hand side vector. And so we have our, first of all, we have our source function here. And so that's 3 times dx times x sub c, okay? And then we add the contributions from the Dirichlet boundary as well. And so we have our Dirichlet boundary of 10. And so when we move those terms to the other side, we have a u multiplied by 10, and then a 2 times k times 10 divided by dx, okay? And so this is how we did the Dirichlet boundary condition on the left-hand side. Okay. And so once again, I know the paradigm or kind of the way of thinking for finite volumes is different. Okay. When we're looping here, we're looping over every single cell. And then each time we visit the cell, we want to check and see, what's going to go on the left edge of that cell, what's going to go on the right side. And so for most cases, you're going to end up as an interior cell. And so you can just plug in our standard formula here. But other times you might be on the boundary. So this is what you do to account for that boundary. Okay, and so next we have the Neumann boundary condition. Okay, and so you can see here for the Neumann boundary condition, since it's on the right, we only make contributions to phi sub c as well as phi sub l, right? And so that phi sub l here is corresponding to this I cell minus 1, right? And here are the coefficients that we add there. And then we add together our source term, which is 3 times x times dx. And then we minus the Neumann boundary condition, which is 3 in this case. Okay, and then finally we come to the interior cell. And so for the interior cell, this is, I think, the simplest case. And so we have contributions to both phi sub c, to the right neighbor and to the left neighbor. Okay, and their coefficients are as follows. And so if you go into the notes and look at our formula, you should see the coefficients match with these, really well. Okay, and then finally, for our interior cells, we also have to add our source function. Okay, so that's 3 times xc times dx. Okay. But we don't have any contributions from the boundary conditions here. Okay, so let me go ahead and run this so you can see what it looks like. Okay. All right, and so in this case, because it's a 1D problem, we can actually plot the exact solution, right? And so you can see here they're very close. And so I believe the amount of cells that I had for this simulation was 10, right? And so with 10 cells, you can see that we approach the exact solution really well, right? So the red is the exact solution, the blue is our finite volume one. Right? Let's see what happens when I increase the grid spacing. And so instead of 10 elements, let me look at 100, and let's see what happens. Right. And so with the 100 cells, you can see here that the two curves are indistinguishable, and so you don't see any blue at all because the two are highlighted, are kind of basically on top of one another. Okay, any questions on 1D problems? Okay, all right, so that's it for 1D. And so the process is the same as our 1D diffusion. It's just that you have to add that extra term for the convection, right? But since we've done the diffusion already, the convection is pretty straightforward. Okay, so let me go ahead and close this. Let me go ahead and share my screen again. Okay, so let's go ahead and move on. And so now that we've done an example on the 1D, we're now ready to move on to 2D. And so this is going to be 2D. convection diffusion, with finite volumes. Okay. And so first step is we're going to write down our governing equation. And so for convection diffusion in 2D, we have the following equation. Right, and true to finite volume style, we're going to write out this equation in vector form. Okay, and so in vector form, we have the divergence of our velocity multiplied by phi minus k times the Laplacian. So Laplacian is the divergence of the gradient, okay, is equal to q at x, y. Okay, and so these are our this is our equation so far. And just like we've done for our previous finite volume examples, we're going to take this equation and integrate it over a cell. Okay. And so if we integrate this, we have a double integral of the divergence of v phi, okay, dA minus k is a constant here. And so I'm going to go ahead and move it out of the integral. But that doesn't change the fact that we have a double integral here. And so we're going to have a divergence of the gradient of phi. Okay. And this is equal to double integral q of xy dA. Right, so all I did was just rewrite the top equation, but I've added a double integral to each of the terms. Okay, and so what we're going to do next is we're going to take this, take these terms right here, and we're going to convert these integrals into line integrals around the boundary. Okay. Okay. And remember, our main mechanism of doing this is our divergence theorem. Okay. And of course, for the source term, we have nothing, we have no divergences there. And so so how we're going to evaluate this is through our trapezoidal rule. Okay. Okay, and so if we perform those conversions, then we end up with the following. And so we have a line integral of the divergence of v phi, okay, dA. Then we have a minus k, or excuse me, I was looking at the wrong line. And so we have a minus k, also is going to be a line integral. Okay. Sorry, these integrals should be ds. And so we have a minus k times the gradient of phi dot product n ds, right? And so those are our two converted integrals. Okay. And on the right hand side, we apply our trapezoidal rule, and we get q of xc yc multiplied by the grid spacing squared. Okay. Okay. Let me pause here for a second. So are there any questions on any of this so far? Okay. All right, so let's go ahead and work on the left-hand side because the right-hand side is basically done, okay? And so remember what these integrals represent. They represent line integrals that you take around the edge of your cell. Okay. And so here's our cell right here. When we go around the edge of the cell, that means we're integrating over this path right here. Okay. All right. And just like before, we can label each of these edges. And so we have a north edge, an east edge, a south edge, and a west edge. Okay. And remember, when we're talking about these things, and they're part of the integrals as well. Okay. And so we're going to have our outward unit normals. Okay. Right, because we need to know what direction points outward from these parts. Okay. Okay. And just like we did for diffusion, right? If we look at our equation right now, although I noticed another typo, I apologize. Sorry, the ice pack is a little bit too cold on my button right now. Okay. Sorry, so this term should be phi times v dot n half. Okay, because if I didn't do that, they'd just be the same as integrals before. Okay. And so what you should see for both of these line integral terms here is that we have to take a dot product between those vectors and the outward unit normal. Okay. And so at this point, it's useful to look at each of our outward unit normals and write out what they are in terms of their components, right? And so for the east outward unit normal, this is going to be a vector 1, 0, right? Because it's just facing to the right. For the north outward unit normal, this is going to be 0, 1. For the west outward unit normal, we're going to have a -1, 0 because it's pointing to the left. And for the south one, it's going to be 0, -1. All right. And so that's important to note. But it's also important to note for us to represent what the v vector and the gradient vector represent. Okay. And so in our equation up there, you can see we have a v vector right there, right? And so if we split this up into components, what we get is our two convection velocities. And so we have the x convection velocity u, and we have the y convection velocity v. All right, in addition to that, we have our gradient. And so our gradient is also going to be a vector. And so this comes from diffusion. And so should be a review, right? So we have partial phi partial x and partial phi partial y. Okay. Okay, so with all these in mind, we can evaluate this line integral on each of the faces of our cell. Okay. Right, and I'm gonna do them individually just because it's quite a lot to write. Okay. Okay, so let's start with the east. Okay, and so on the east, we have integral on the east edge of phi v dot n minus k gradient of phi dot n, okay, ds. All right, and so if we take the dot products and we apply our trapezoidal rule, we end up with the following, right? And so first we have phi, and so we're gonna have phi sub little e, right? And so that's gonna be the value of phi evaluated on the east edge, okay? And then we have v dot n, and so v is u comma v, and we dot product with the normal vector, and we just get u, okay? Right, and so this u here was a result of v dot n hat, okay? Okay, and then we have k, we have a minus k, as the minus k is a constant. And then we have gradient of phi dot product with n, as we again look at our gradient of phi, and when we dot product with 1 comma 0, we end up with just the x component of that. So we have a k partial phi partial x evaluated on the east edge, okay? And we're going to multiply this by delta y, because the delta y comes out due to our trapezoidal rule. Okay. So that's the first integral. Okay. Any questions on any of this so far? Okay. Okay, so let's go ahead and do the other 3 integrals now. So let's do the south one. So the south one, we have, I don't know what did I do south next? That's weird. Okay, whatever. And so we have integral on the south edge of phi v dot n hat minus k gradient of phi dot n hat ds. Okay. Right. So first we have a the term phi, right? And so with phi evaluated on the south edge, that's going to be phi sub s, okay, phi sub little s. And then we have the dot product between v and n hat for the south, right? And so since the n hat for the south edge is -1, 0 comma -1, then when we dot product them together, we have a minus v. Okay, and so the first term is going to be a minus phi s plus v. Okay. All right, so next we have a minus k gradient of phi dot n hat. Okay, once again we have a dot product with n, and so we have a minus and a minus. They're going to cancel out, and so we end up with a plus here. Okay. Okay. And so we have a plus k partial phi partial y evaluated at the south edge, and all this is going to be multiplied by delta x. Okay. Okay. And so we have the west and the north left, and so I'm going to go through these a little bit faster. Okay. So for the west, we have phi v dot n hat minus k gradient of phi dot n hat ds. Okay. On the west side, our unit normal vector here is -1 comma 0, and so we have a minus vw u plus k partial phi partial x. That on the west, okay, delta y. And finally, we have the contribution on the north side. And so this would be integral on the north, okay, phi v dot n hat minus k gradient of phi dot n hat ds. Okay, this is equal to, we have a positive phi n v minus k partial phi partial y on the north face multiplied by delta x. Okay. All right, so we have these four integral expressions here. Okay. All right. And so the next step that we're going to do is we have all these phi values and all these slopes, but those are in terms of the face values, in terms of the edge values, right? And so we want to put these in terms of the self-centered values. So we're going to plug in for all of those as the next step. But before we do that, are there any questions on this? Does the signs of all the terms make sense to everyone? Because we have quite a few negatives and stuff kind of floating around. And so, make sure you kind of double check all the signs to make sure that they make sense to you. Okay. All right. So our next step is we want to put these. We're going to put these in terms of the self-center values. Okay. And so there's 8 that we need to plug in for here. And so let me go ahead and list all of them. Right. And so first, let me draw our little D-pad here. Okay. Right. So there is our little D-pad, right? And so the cell in question that we're developing these equations for, this is of course phi sub c, okay, C for center. And on the north side, we have phi sub n. On the east, we have phi sub e. On the south, we have phi sub s. Okay. And on the left, we have phi sub w. Okay. And so we want to put our equations in terms of these expressions, but we don't have them yet. Okay. And so I'll show you a couple. It's kind of a lot to write down. So I'll show you a couple of what we do, but these are just merely extensions of what we've done in one dimension. Okay. All right. So first we have phi sub little e, and so that's the boundary value or the edge value that's between phi sub c and phi sub e. Okay. And so if we assume that we use a central difference, it's going to be phi sub c plus phi sub e divided by 2. Okay. And then if we take the slope of the line that connects those two solutions, right? And so that's partial phi partial x on the east edge. And so this is going to be phi sub e minus phi sub c, all divided by delta x. Okay. Okay. Let me do just one more because they all kind of follow the same trends. So let's do the ones on the south, right? And so for the south, right, phi sub little s is going to be, that's the edge value that's between phi sub c and phi sub big S. And so this is going to be phi sub c plus phi sub big S divided by 2. Okay. And then we have partial phi partial y on the south face. And so this can be phi sub c minus phi sub s, all divided by delta x. Okay. Or delta y, excuse me, because we're taking the derivative in terms of y. Okay, and so I think from here, I think you could kind of fill in the blanks for what phi sub little w, phi sub big N are. Okay, but what we're going to do is we're going to basically substitute these in to all of our expressions up here. Okay. Okay. All right, so we're next step is going to be plugging in. So it's going to be quite a bit more writing, but at the end, we're going to get our algebraic equation from this. All right, any questions on this? Okay, so let's go ahead and plug all of these in. Okay. Right, and so for the east integral, right, first thing that we had was we had a phi sub little e times u, times delta y, right? And so we're going to have a phi sub c plus phi sub e divided by 2 multiplied by u, okay, minus phi sub e minus phi sub c divided by delta x times k. Okay. And the whole thing is multiplied by delta y. Okay. And so for the south, we have a phi sub c plus phi sub big S divided by 2 times v minus sign, excuse me. Okay. Right, remember we have that minus sign there for the south integral. Then we have a plus phi sub c minus phi sub big S all divided by delta y times k. And the whole thing is multiplied by delta x. Okay. Let me make this negative a little bit bigger. It's a little bit small. Okay. And so that entire first term there is negative. Then for the west integral, what we have is minus phi sub c plus phi sub w divided by 2 multiplied by u plus phi sub c minus phi sub w all divided by delta x, okay, times k. And this entire thing is multiplied by delta y. Okay. And the last one we have here is the north side. And so this is going to be a positive phi sub n plus phi sub c all divided by 2 multiplied by v minus phi sub n minus phi sub c all divided by delta y k all times delta x. Okay. Okay, and so that's what we get from plugging all of it in. And so you know, it's a lot, right? And so now that we have convection and diffusion, there's quite a bit to take care of here. Right? All right, and so the last step, you know, to kind of put all this together, remember, you know, the reason we got these 4 integrals was because you know, we took our one line integral, which is supposed to go around the entire edge of the cell, and we broke it up into 4, right? And so to put them back together, all we have to do is just add all of these together. But the reason I did this is you know, I really want you guys to think about these in terms of the 4 integrals, okay? And this is going to be important later on once we start to do 2D finite volume equations. And so what you'll see is that, you know, I'm going to change the structure of the code a little bit for the 2D finite volumes to make it really clear that, you know, we're doing each integral kind of one by one. And so, you know, I formatted it in this form so that you can kind of see, you know, what each of the integrals kind of brings to the table. And so I'll add them all together to give you one equation here, right? And so that one equation will be useful when you do problems by hand, but when you do problems with code, you know, the 4 expressions that you see above here, you know, that's going to be more useful, and that'll be more clear, you know, once we do an example. And unfortunately, I think today we're not going to have time to do the example, but you'll see next week once we do the code. Okay, so there will be kind of distinct portions of the code which correspond to, you know, the west integral, the east integral, the south integral, and the north. Okay, and so if you add all these together, and I'm going to go ahead and combine a lot of the terms, and so I'm going to go ahead and do the simplifying a little bit for you. You end up with the following one algebraic equation. Okay, so first you have a u times delta divided by 2 minus k times phi sub e. Okay. Oh, and I've also assumed that we have even grid spacing in the x and y direction, and so we have a delta. Okay. Plus minus v delta divided by 2 minus k phi sub s, okay, plus minus u delta divided by 2 minus k phi sub w, okay, plus v delta divided by 2 minus k phi sub n, right, plus 4k phi sub c is equal to q at xc yc delta squared. Okay. All right, and so this is our finite volume equation for 2D convection diffusion for an interior node. Okay. Interior cell, excuse me. Okay, and so if you have a problem, if you have a problem that you work by hand, you can start with this equation here. Okay, for the interior cells. Okay. Any questions? Any questions on this? Okay. All right, so now that's how we take care of the interior cells. And so, the next step, of course, is how we handle boundary conditions. Right? And so this is not going to be too different from how we did 2D diffusion, except now we just have the convection term that goes along with it. Okay, so that just adds a little bit extra step. All right, so let's take a look at the boundary conditions. And so we'll start with Dirichlet ones. Okay. And the way I'm going to do these is a little bit different. And so instead of tackling the entire equation like above there, one way that you can look at the boundary conditions in 2D is that you only on whichever edge that you have a boundary condition, you're only going to modify that integral. Okay. Okay. And so, when we go over these, I'm not going to go over the entire expression like this again, but the assumption is that, if you can derive how that specific integral changes, then what you do is you just add it together to all the other integrals that stay the same. Okay. Okay. And so basically you're going to follow the exact same process that we just followed for the interior cells, except that, let's say that you have a boundary condition on the east one, right? we would take this expression here, replace it with the integral expression that accounts for the boundary condition. Okay. And then add it together to all the other integrals. Okay. Okay, so let's look and see what that looks like for a Dirichlet boundary condition. Right. And so let's look at a case when we have a Dirichlet boundary condition on the north edge. Okay. Okay. All right, so here's phi sub c, and on the north edge we have phi naught, which is known. Okay, so that's our Dirichlet BC. Okay. Right, and those are all neighboring subs. Okay. And so for this case, because we only have a Dirichlet boundary condition on the north, the only integral that we have to modify is the north integral. Okay, and so our north integral, right? Our north integral is the following. So we have phi v dot product with n minus k gradient of phi dot n hat ds. Okay. Right, we're going to modify this to account for that known value, right? So normally when we do this, right, and we evaluate this first term, what we have is phi sub little m multiplied by positive u. Okay. But we already know what phi sub little n is, right? Because phi sub little n is basically, whoa. I have no idea what happened there. Okay. And so phi sub little n is just the value of phi at that boundary, right? And so instead of phi sub little n, we're going to replace this with phi sub naught. Okay. Right. And so that's kind of a very elegant kind of transition into that. Okay. Okay, so now let's do the diffusive term. And so for the diffusive term, right, this is the same as before. And so we're going to have a minus k. And then we're going to take the slope of the line. And so we're going to have phi sub naught minus phi sub c, all divided by delta y divided by 2. Okay. Remember, we have delta y divided by 2 because the distance is shorter, right? And then we're going to multiply that by delta x. Okay. And so if we simplify this expression right here, you'll see that we have some contributions to phi sub c, but most are going to be right-hand side known values that we're going to move to the other side of the equation. Okay. And so if we simplify, and so our north integral here is going to be 2k phi sub c, right? Plus phi sub naught times v. Oh, there should be a v right here for the velocity. Okay. Phi sub naught times v times delta. Okay. Minus minus 2k phi naught. Okay. And of course, one assumption that I made was that the grid spacing was the same between x and y. Okay. And of course, anything with phi naught here is known. And so these two quantities, we'd move it to the right-hand side of the equation. Okay. Okay. And so this is our new expression for the north integral, right? And so our north integral is just going to be 2k phi sub c plus phi naught v delta minus 2k phi naught, okay? And so instead of the north integral that we have up here, right? Which involves phi sub n's and phi sub c's, we would replace this with what we just found out down there, okay? But then all the other integrals, we would compute them as normal and then just add them all up, and we would get a new algebraic expression here on the bottom. Okay, any questions on this? Okay. All right, so that's Dirichlet boundary conditions. And so very quickly, let's do Neumann boundary conditions, because Neumann boundary conditions are easy to do in finite volumes. Okay. As for Neumann boundary conditions, we're just going to replace the entire integrand with the flux value. Okay. And so, for example, let's say that we have a Neumann boundary condition on the east. Okay. Okay. And so here is our cell. Okay. We have a north neighbor. We have a south neighbor and a west neighbor. Okay. And on the east side of the cell, we have a prescribed gamma. Okay. And so since we only have our boundary condition on the east, we're only going to modify the east integral. Okay. Okay. And so our east integral here is phi v dot n hat minus k gradient of phi dot n hat ds. Okay. This entire expression in the integrand here, right? We have a contribution from convection and a contribution from diffusion, right? This represents the flux of our quantity across the east edge. Okay. Okay. And so if we're prescribing our flux with gamma, then what we can do is we can replace this entire expression here with just gamma. Okay. All right. And so our east integral then is very simple. And so our east integral becomes gamma, right? And we have to multiply by delta because the delta comes out from the trapezoidal rule. So we have a gamma times delta here. Okay. And so it ends up simplifying our expression quite a bit. Okay. And then just like we saw with the Dirichlet boundary condition, all the other integrals are going to stay the same. The north integral, the south integral, the west integral. And so all you would have to do is just add this together to all the expressions up there that stay the same. Okay. All right. Any final questions on this? Okay. All right. And so that's the basics of 2D convection diffusion with finite volumes. And so when we pick this up on Monday, we're going to do an example. And so the example will kind of pull everything together, and you'll see kind of a lot of these techniques in action. Okay. All right, so have a great weekend, everyone. Thank you guys for meeting virtually today. I appreciate the flexibility. And so remember the homework's due tonight. If you have any final questions on it, I'll try to be online tonight as much as I can to answer questions. And I will see you guys next week. Thanks, guys. Yeah, thanks, Eddie. Yeah. Hopefully my back is better by next week.
Yeah, I hope so too. Thanks again, Dr. Tran.
Thanks, guys. Have a good weekend.
You too.
I have a question.
Sure. What's up?
It's like totally not from the homework or from the notes.
Yep.
So I was thinking, like imagining like a perfect square and it's split up evenly, right?
Yep.
And but there's like an empty space in the center. I was
Hmm.
thinking if there could be like a boundary condition. Could
Yeah.
be like either Dirichlet or Newman.
Oh, absolutely. Yeah, you can
Yeah.
definitely do that. Yeah.
Oh,
and
okay.
so, with 2D, you have a lot more flexibility with the domain. So you can have like holes in the domain and you can apply boundary conditions there and everything like that. Last year, actually, the project was something like that as well, because I basically cut out a little hole in the middle. It was a little bit similar to your guys' project, but the situation from last year was I had them simulate a gas leak. And so I cut out a hole in the middle of the domain and I said, gas is leaking from this hole. And so I applied a Neumann boundary condition there. And they had to simulate that for their final project.
Oh, wow.
Mhm.
Interesting. Well, thank you, Dr. Tran.
Yep, no problem.
Bye.
See ya.